Welcome back to module 4. In this module, we have been presenting the connection between quantum mechanics and linear algebra. And just now we have presented the basis set approach to quantum chemistry. In basis set approach to quantum chemistry, we have presented that psi x can be expanded in the basis of phi I. And the reason why we can write down this, because we have pointed out that if phi I living in the Hilbert space, in the same Hilbert space, psi will also live, because the linear combination of the wave functions living in the Hilbert space will also live in the same Hilbert space. So, that is the basic idea behind the basic mathematical idea behind behind this linear combination. Now, when you do this linear combination with respect to this phi I basis, one can present this psi as a column matrix with its components C1, C2, C3, and we have said that this is going to be for the reduced Hilbert space, where we have truncated this infinite summation to some certain number n, and that is the way we can represent. So, when we represent, this is basis set representation of the wave function. Wave function can be represented in terms of a column matrix. Now, when we represent it, implicitly we assume that it is with respect to phi I basis. If I do not, if I change the basis to something else, let us say chi, then this coefficient will also change. So, this is going to be then let us say B naught. So, this is going to be B I, and then all this coefficient will also change. However, wave function is remaining to be the same. So, which way we represent the wave function, with respect to what basis we represent the wave function, it really does not matter. All we need to think about is that what kind of coefficient I get, and the question is how do we evaluate the components expansion coefficient if the basis is known. So, that is the point we are going to address here. If I have the known basis, then as usual we will expand psi x as linear combination of, I am not writing here something n or infinity, because it is all equal now, equivalent, because we have said that Hilbert space, infinite Hilbert space and reduced Hilbert space will give me the same properties, and rigorous mathematics can be used to prove that, and we will not get into those detailed mathematics. We will just move forward with this demonstration. How do I get this Ci if the basis is known? And we can get it done, and we have to remember that this basis phi I, this basis are orthonormal basis. What does it mean? It means that if I do this integration phi I star phi I dx, this is going to be 1. But if I do this integration minus infinity to plus infinity phi j star phi I dx, this is going to be 0. So, what we are assuming that we are expanding total wave function in the basis of orthonormal wave function, and if we do that, then we can use a trick to find out Ci. How do I do that? I will first multiply this equation, this expression by phi j star and then I will integrate it from minus infinity to plus infinity over the entire space. We are continuing with one dimensional problem. One can understand, one can develop the understanding with the help of one dimension, and then we can translate that idea to three dimensional problem as well, and we will do it at a later stage of this course. So, we have we are using this trick, and this is a trick which we will be using in many occasions. So, we have picked up. So, we had a basis phi I, which means phi 1, phi 2, phi 3 dot dot dot, dot phi j dot dot dot. So, phi n, all these basis functions we have. What we have done, we have selected particularly one phi j and then multiplied phi j star from the left. So, we are multiplying from left, this is a multiplication. Left and then integrate. Phi j star is multiplied from left, and if we do that, then what I get here is that C I, summation of C I equals 0 to some number minus infinity to plus infinity, then this is I have phi j phi I dx. So, this summation is going to be now C I, this is delta j I, and when I do that, all values of delta j I would be 0 if I not equals j, but if delta j I would be 1 if I equals j. That is the orthonormal basis, the property of the orthonormal basis, and this property exactly coming from the property of the Hilbert space. Hilbert space property of the Hilbert space suggests that its inner product should exist, and so what we get is that the entire summation will be 0 except for this C j term, because in C j delta function will take the 1 value. So, I get this C j value. So, jth component. So, from this exercise what I have learned is that C j, jth component is given by this integration minus infinity to plus infinity phi j star psi dx. So, one can say it is instead of jth component, one can generalize it for ith component also, it does not matter, or first component, second component, everything. So, phi 1 sorry C 1 I will get C 0, let us say C 0 I will get, how do I get that? C 0 I will get it minus infinity to plus infinity phi 0 star psi dx. C 1 I will get minus infinity to plus infinity phi 1 star psi dx. C 2 I will get it minus infinity to plus infinity phi 2 star psi dx. So, this is the way expansion coefficient. So, once we get this expansion coefficient, I can express psi as C 0, C 1, C 2 like this, and I can represent in the matrix form. This matrix form, I will repeat one more time, this matrix form is obtained with respect to certain basis is phi I. If I change the basis, immediately these components will change, but it does not change the wave function, just like the vectorial example we have given. But then question, our next question is, from this exercise we have understood that we can find out the expansion coefficient, but what kind of basis we should select, and this has two answers actually. What kind of basis we should select for our work. Each basis function phi I may correspond to this phi I. So, psi is represented by some expansion coefficient I and phi I. So, this is the basis function, and question is what kind of basis we should select. Phi I, this basis function, may correspond to the orthonormal eigenstates of the zeroth order Hamiltonian of the system. And how do you get that? Before I have been mentioning this one from the beginning, that I have this time dependent Schrodinger equation, and under variable separation method we immediately get this time independent Schrodinger equation, E psi. But when we get this time independent Schrodinger equation, we get a solution with associated with a particular state. So, this equation gives me a set of solutions. These are the eigenstates of the system. This is the just like if you think about particle in one dimensional box, we solve this time independent Schrodinger equation and we have got n equals 0 state, n equals 1 state, n equals 2 state, like this way we have got this. Each one is representing the eigenstate of this time independent Schrodinger equation, and that is what we call zeroth order Hamiltonian. The Hamiltonian which doesn't include any external potential. It is just we have considered the Hamiltonian of the system. So, for one dimensional particle in one dimensional box, it should be then just a kinetic energy operator. And so this each state is the eigenstate, and because we get entire state, a set of states, these are called the spectrum of the system. This is called spectrum of the system, spectrum of the Hamiltonian or spectrum of the system, quantum system. So, why it is spectrum? Because based on this eigenstate we find out what kind of transition I can have from one state to the another state. Generally we use this kind of transition in chemistry to explain the spectroscopy. So, that is why it is called spectrum. Now, one can use those eigenstates to expand the total wave function, and if we do that, then it is called spectral basis. Then I have this phi I. So phi I. So, if I take the phi I, the basis, if I use this eigenstates or the spectrum of the Hamiltonian as the basis to expand my total wave function, then it is called spectral basis. But and what is the property of the spectral basis we have? We know that each function is representing the eigenstate or eigenstate of the Hamiltonian, and each function by its own nature is delocalized. So, for an example, I have shown it here as a schematic representation of the spectral basis. I have total wave function psi here, but psi has been represented by different wave function obtained from this phi I. Let us say this yellow one is phi 1, this brown color one is phi 2, then bluish color one is phi 3, this green color one is phi 4, and one thing is quite clear, they are all delocalized in space. So, spectral basis by its own nature, it's all are delocalized or global in nature. This is the property of the spectral basis. If I take that the spectral basis. So, spectral basis is directly coming from its own spectrum, its own the system's its own eigenstates, and based on that eigenstates also we can represent this. So, this is one way to represent the total wave function. However, the spectral basis approach requires a very large number of eigenstates phi I and integration over the eigenstates, because finally I have to find out C I, and C I, the definition of C I have given already. This is going to be phi I star psi dx. So, I have to integrate a particular thing to get my coefficient. So, to represent the spectral basis, it becomes little difficult, particularly when it comes to the numerical implementation. So, direct numerical implementation of spectral basis is far from straightforward. This is why almost all currently available numerical methods for solving TDSE do not make use of spectral basis. Spectral basis is avoided generally. We do not try to solve the Schrodinger equation, time independent Schrodinger equation, and get that function and then use it for the solution, for getting the solution. Rather, pseudo spectral basis is used under the grid representation. So, these are the two important concept we have given. Pseudo spectral basis, what does it mean? It looks like a spectral basis, but only difference between a spectral basis and a pseudo spectral basis is that all pseudo spectral bases are localized. You see this one more like a delta function, this one at a different position. So, and pseudo spectral basis is used under grid representation, under grid representation. Now, grid representation, we have already shown grid representation in one of the Python tutorials in this course. I will just one more time repeat. What we would like to do, I have the problem domain, this is the x axis, that is called problem domain or the position space in one dimension. This position space I will just divide into a small segments on small grids, this kind of grids I will divide it. Each grid is separated by delta x difference, and now I have the total wave function which is psi. So, what I will do right now, I will represent this the entire psi, which is a continuous function. By its nature, a wave function is going to be continuous. But under grid representation, a continuous wave function is expressed on a set of position grid points. So, what I have, instead of this wave function, continuous wave function, which is represented by this dot line, I will have certain values of the wave function on these grids. And that is the way I am going to represent the total wave function. It will be like this. And amplitude of the grid points amplitude at the grid point represents the coefficient of localized basis function. So, what we are doing here is that I have this now psi under grid representation. Psi would be represented as summation of C I delta J I, this is I equals 0, starting from I equals 0. So, delta function, so each one, so at each grid point I have now delta functions assigned, and the coefficient C I is the amplitude, this one, the length of this amplitude. So, in the end what I get is that I will get psi x 0 point, at x 0 point I will get the coefficient C naught, at psi x 1 point I will get the coefficient C 1, at psi x 2 point I will get C 2, and so on, like this way. So, in the end I will be able to represent the wave function in the matrix form, and it is going to be similar to the spectral basis form, but only difference is the nature. So, the matrix would look like following. I have this psi which is going to be C 0, C 1, C 2, C 3, C 4, like this, and this is called discretized wave function on the x grid. So, what does it mean by this C naught? C naught is this value, then C 1 is this value, C 2 is this value, C 3 is this value. For just pictorial representation I have made them very well separated, x naught to x 1. It may give you an impression that we are going to separately use that, I mean we are going to use such a big separation, but remember delta x will be selected to be very small. So, they are not heavily separated, they will be very close to each other. So, that we can use a huge a big grid grid points, a large number of grid points, and we can represent the wave function. It is the value of the wave function on those grids. So, it is representing a function values on those grids, and my the form of the spectral basis pseudo spectral basis is going to be like this, a delta function represented by this and then C I value. So, once a wave function is represented by a column matrix using pseudo spectral basis approach under grid representation, next important question is following: what is the matrix representation of quantum mechanical operators under grid representation? So, in the grid representation, if wave function should look like this, then we have to remember that in the end I have to employ Hamiltonian operator on the psi. So, what would be the matrix representation under grid representation of this Hamiltonian operator which will be acting on this wave function psi? So, that is the next question we have. what is the matrix representation of quantum mechanical operator, because I have to operate this wave function Hamiltonian operator on this wave function. So, I need to find out the matrix representation of the Hamiltonian operator. But before we go ahead and find out what is the matrix representation of Hamiltonian operator, because we will be using the lot of matrix algebra in to find out the ultimate form of a matrix representation of the Hamiltonian operator. We will briefly go over the matrix algebra first, because we will be using matrix algebra to find that out. In linear algebra, a matrix represents an array of numbers, a collection of numbers or mathematical expressions arranged in rows and columns like this. We are almost most of us are quite familiar with this matrix representation. Just to remind, what does it mean by this? These are the columns we have, and these are the rows we have, and these are the columns we have. And matrix can be of the order of m by n. And when we represent a matrix, certain rules are followed to carry out algebraic operation with matrices. So, what are the rules we have? Matrix is nothing but is a collection or array of numbers or mathematical expressions arranged in rows and columns. So, M representing the row and N representing the column. So, first we will write down the row and then cross N, row cross column. Matrix addition, that's one simple algebra we do with the matrices. How do we add two matrices? Let us say I have first matrix is A11, A12, A21, A22, and another matrix is B11, B12, B21, B22. We can add them as corresponding elements are added. So, I can add A11 plus B11, A12, B12, A21, B21, A22 plus B22. Corresponding elements are added. Scalar multiplication, if I have a matrix like this A11, A12, A21, A22, and if I multiply by lambda some scalar value, then it is actually each element is multiplied. So, lambda A11, lambda A12, lambda A21 and lambda A22. So, each element is multiplied. Matrix multiplication and scalar multiplication, these are the two concepts. We have to distinguish these two concepts. Previously we have shown scalar multiplication, here we will show matrix multiplication. I have again two matrices, a simple matrix, 2 by 2 matrix we are considering, because that will give us a direct visualization what might happen. A21 and A22. I am just matrix are represented. If it is A, then we just cover it like this way. We are representing like this way. So B matrix is B11, B12, B21 and B22. So if I multiply these two matrices, matrix multiplication will give me in a following way. Little complicated, we will go this way and we will go this way. So what does it mean? I will first multiply this one and this one. So A11, B11 plus I will multiply this one and this one. So plus A12, B21. Second one, I will multiply A11, B12. So I will multiply this and this plus I will multiply this and this. So A11, A12 plus B22. Next one, I will multiply this one, A21 and this one, B11 plus I will multiply this one and this one, A22, B21. Similarly, I will multiply this one and this one, which is A21, B12 plus A22. This one I will multiply by this one, B22. Matrix multiplication is little complicated, but if we understand the order, we have to follow always this order and we multiply and add them. So final matrix elements matrix multiplication requires little bit more practice to do it quickly. Final matrix elements are represented by IK is going to be summation of j equals 1 to n a ij b j k. That's the rule one should follow for the matrix multiplication. Transpose of a matrix obtained by interchanging rows and columns. So I have to do A ij. If I do transpose, which is expressed by T transpose, then this is going to be A j I. I just change the so if I have a matrix like this, A12, A22, A21, A this is going to be A. This is A11, this is A12, this is 21 and this is 22. If this is the matrix, then transpose of the matrix will be given by this. I just change the row and column, interchange the row and column. So, this is remaining to be the same, but this one will change. This is going to be 2 1, then this is going to be A 1 2, this is going to be A 2 2. That is called transpose of a matrix. Therefore, transpose of a column matrix is a row matrix. So, if I have a column matrix like this, A1, A2, A3, then transpose would be A1, A2, A3. A column matrix will be converted to row matrix, and this kind of column matrix are called vector in linear algebra. We will stop here, and we will continue this discussion of this module in the next session.